Today we have the topic high-level synthesis. It's another tool which is becoming more and more relevant in FPGA design, also in ASIC design actually. And we're going to look how this all works. And today, and it's the second last topic, so it's actually the last actual topics of tooling you're going to have in this course. And also the seminar, and this will be kind of a recap seminar. So you're going to use high-level synthesis to do all the above kind of things in one kind of project and whatever you can do or want to do. And in a small scope, so I do not expect you to write a lot of code, but it's about the process so that you can do your own project essentially. And that would be the last. This will give you a lot of points. You can be able to miss some of the previous assignments, but most likely you will need the last assignment to pass the course essentially, or at least some of the points. So there will be some point. I will introduce this, but there will be some points on the concept and on doing different steps. And then the last one is going to be next week. Is the last topic of the course. It's basically an outlook into modern tool beyond high-level synthesis, or how this is being used further, and whoever is interested in like follow-up projects. And there will not be a dedicated seminar because we're going to be talking about the previous seminars and the previous assignments. So that we wrapped up the course essentially. So lecture goals for this one. So high-level synthesis is always abbreviated as HLS. It's like why and when should we use it? What is it? How does it work? And what are limitations, challenges, applications, design patterns best suited for it? What tools, co-simulation and verification? What do these terms mean? And then impact of system-level design and integration, and how do design decision and constraints affect HLS outcomes? Maybe not exactly in this sequence, but basically our overview is from definition to design workflow to decisions. We're going to have a short comparison to HDL design, plenty of limitation and challenges, so it's going to be a huge block of things again, and then integration, verification, and last application areas to see what you can do, where does it make normally sense to use HLS, and where is it less useful. The definition and motivation. Basically, we all know that VHDL or System Verilog is quite complex, so we want to describe it in an easier way. Ideally, our design would be done, but then we are in a processor, and then we have less flexibility. So we have here an intermediate thing called high-level programming, high-level programming languages. For everyone else, this C and C++ is not high level, but for chip design is very high level. Although we have tendencies that they come slowly Python in there in a sense, but that's a totally other story. Right now we have C and C++ and some system C. We'll see how this all works. And basically we want to describe our hardware on these language levels. And basically the HLS tools generates register transfer levels code, so HDL code, hardware description level code, from the high-level design written in C or C++, or derivatives of it. The motivation is that we have HDL provides full control, so we can do anything we want to do, but it's very time intensive, and then we of course can also make a lot of errors, and that's why we have the extensive simulations and so on, but it's still error prone, so you got to be very careful. HLS enables for a chip design very rapid prototyping. So basically, because we do not have to write anymore the low-level hardware details, focusing on algorithm development. But that also means that all the things which we learned at the beginning of the course, that in VHDL I can decide how big my vector is and all these kind of things, that is much, much more limited because I'm going to work with integers or int 8, int 16. So that's not going to be as efficient anymore. But it's still going to be much faster from a development time. It's especially used for frequent design iterations. So when I need to quickly work over and over my algorithm, and I want to figure out how can that work, and then for complex data path oriented computations like image processing, artificial intelligence, machine learning, or signal processing. Especially image processing, signal processing, they are very commonly used. AI we're going to come to. Also next lecture, there's these days other tools to do this mostly. And Yes. So you always, when you want to draft something, or you do not need the maximum performance for it, but you want to be rather fast or have a development cycle, image processing continuously changes every year. So if you would do a VHDL, you're going to spend a year. And then the next algorithm comes, or the next GPU comes out, and then you can't compete anymore. So that's usually what it's being used for. Then we have increasing relevancy of HLS. So a lot of different domains. There's various reasons. In a nutshell, it's because FPGA design becomes more and more relevant. It's not anymore like in the past that you have like one-time flash FPGA designs. You have very, very flexible chips which you can flash as often as you want. This is even being integrated into servers, so you can actually have on a server, on a cloud, you can require FPGA access, and then you can program your own hardware onto it, and then you can have different applications accelerated, which a GPU or no other chip could do. So for this, we of course have then a lot of new demands, so it becomes much, much more versatile, but it also means that more and more people want to do larger and more complex designs. And if you think about you working on a logic level, on like a byte level in logic, then this overhead becomes bigger and bigger. And you need to consider that in modern FPGAs, they have millions, hundreds of millions of logic elements. And then this is just very, very high of a complex overhead. And efficient, it becomes very difficult to make HDL efficient and to keep those balances. Because we always talked in kind of absolute terms so far. I want to have a very performant or a very low area or a very low power. But if I have such a big chip, I may not want the full power or I want to have a balance. And if you do this in VHDL, you would need to have on this level like a mix of, or this IP core I'm going to make very, very fast. This one make very low power. This can be possible, but you see it becomes yet another level of complexity, because you're going to have to decide, where do I save resources and where do I save time, for example, or where do I save power. So this becomes much, much more difficult to balance on a very big design, besides obviously the huge design effort to design millions of logic gates. Luckily we have IP cores, but still it's much more than what you could do in a very big overhead. And basically what we do here, we make we give more constraints on a higher level. We say the tool should optimize towards certain directions, or towards performance or power, or this balance, and then we can focus on functional correctness. So we just want that our algorithm is accelerated and works, but we do not care about the last few percentage of performance which we can gain. Time to market is actually probably the biggest part when we talk about cloud. I want to quickly run something on my cloud. I do not want to sit there for a year or two to develop my IP core. I want to write it in C and try my acceleration out. So especially AI and machine learning or networking products, 5G, 6G. Before 5G is even out, the industry is talking about 6G developments. So this is a very fast product cycle. And there the performance matters really. So you go into FPGAs, or especially early prototyping. And basically you have an increased development efficiency by enabling reusability of software algorithms and just putting them into hardware. So you need to only do minor adaptations from your original algorithm, which is of course what you want to have. So I want to write an algorithm and I want to use it everywhere and not have to rewrite it. Demands for productivity. I guess it's kind of, when you get more and more complex design, more and more time to market pressure, you need to be more productive, more effective, more efficient in your time usage. So this was HLS enables. And then basically you can use, as said, C++ code bases. And basically the part is there is a learning curve. We're going to come to this later. But basically the learning curve to introduce designs into FPGA is with HLS less steep than with FPGA designs in itself, or VHDL designs, or HDL designs. And that's what this course is kind of about. It does not matter for the workflow later, if you're not much at least, if you're going to use VHDL or HLS, because you're going to have still to go through synthesis, placement, routing, and simulation. So these things are still there. That's what we have in the course. So this will all be useful, but there's a tool where you may write an algorithm especially. And stability and rapid prototyping it's basically for iterative design. So when you want to go fast, and I want to have this algorithm, I want to have this algorithm, I want to have this and this feature, and that's basically very important when I have functional developments over time, evolving over time. Here, very briefly, a workflow comparison. It's not the only comparison which we're going to have. In HDL, we have like an algorithm or design description in hardware description language. So in VHDL or Verilog, we have then an RTL simulation debugging, as you know, and then we have a synthesis to hardware, so synthesis simulation again to verify placement and routing, timing analysis, and last simulation, and we do the bitstream. So this is pretty straightforward, but we have here on this one layer. The difference in HLS is that it's unfortunately not here on the same level now, but we have here a high-level language input. So we write on a higher language, then the HLS tool generates actually the VHDL code and compares the C output to the HDL output, and then says we have a co-simulation, and then we get out of that, we get our register transfer, so VHDL or Verilog. So we basically get this output, and that can be compared, and then we can go afterwards. We can load this IP core in Vivado, for example, and then we are back to the normal workflow of using the IP core for RTL simulation and synthesis to hardware for the last steps.
What about debugging?
Yes, this is split over both of them here, because here you would care about the functional correctness, right? So that my C code is the same as what is being not synthesized but generated into RTL, and here is the low-level debugging. It's true I should have maybe written this into both, but it happens over both steps. Here it happens only after I've written my full design, actually. HDL design workflow in detail. Basically, on a high-level language input, I provide C, C++, or System C. And usually the code consists of data processing algorithms, loop structures, function calls. It looks very much like software, or you could call it software code. But there will be so-called pragmas, we're going to come to this, which you're going to use to describe what processes I now want to use for optimization. And you see already here the workflow is a bit different. You do not, in VHDL, if you remember, there's much more architecture things. So you care about which interfaces I use, how they connect to each other. This all, besides functions and function calls and return values as you have in C, C++, this is not going to be a thing anymore, which is good and bad at the same time, right? Like you don't have to take care of all this interfacing and this hierarchy, but you cannot. So you lose the benefit of that as well. The HLS tool for code simulation and RTL generation, there's plenty of them, but every vendor has kind of their own. And basically for AMD Xilinx, we have Vitis HLS. That's why I let you install in the beginning of the course Vitis as well, because we're going to need that now. And then Intel HLS was basically a competitor, which I've not heard that much about because I've not worked with it, because Intel devices are much rarer in space technology. Catapult HLS I've heard a lot about, I've never used unfortunately, but it's also used for ASIC design. So you can actually do your full chip design, actual chip design in C, C++ if you want. So that's provided by Siemens, or Siemens bought that years ago, and it's one of their product portfolios. So Siemens does actually a lot of chip design. Also model sim, so the simulation, whatever it's called now, QuestaSim, or whatever it's called, is also owned by Siemens. So Siemens is very powerful actually in the chip design domain. Then we have translated high-level language description into, RTL code, so VHDL or Verilog or System Verilog. And here it comes basically to refine the HLS code beyond what we have written as functionality. We use directive called pragmas to optimize the hardware output. So we can do certain functionalities to reduce area or what we want to do, or interfaces to get what we want. The RTL simulation is simulated and verified to ensure correctness with the original algorithm in VHDL, and then design moves to synthesis implementation, working into the traditional workflow. And that's basically in the assignment, in the seminar, I will show you that, and probably will do it in the assignment as well. You export from your AHLS tool the IP core, and you load it into Vivado as a normal IP core, and then you work with it. Maybe sometimes when you do it, well, you just have to connect everything with the pins up, but maybe you want to add the UART or Ethernet interface into your design, and then we have everything working together. I will give you a short example in the seminar for this, so you can see that a bit. So, tools and languages, kind of already touched on it. Just now concise on one slide. So this lecture is a lot of like content which I will repeat in various aspects and then summarize into each of the slides. So you have tools, already said, you have Vitis HLS, supports CC++ and System C, so it's the most diverse tool actually. It's basically FPGA specific RTL, and basically Vivado jumps in later stages to support the actual hardware deployment, so the bitstream and the implementation. Intel HLS compiler works for Intel/Altera. So what AMD did with Xilinx, Intel did with Altera years ago. So you have the same thing here. Although I do not remember that Altera back then had an HLS tool. So they developed this in-house to be competitive. Of course, there's also, Microchip has also their own HLS tool. There's open source HLS tools. I might come into that in the next lecture, like tools and how the different workflows interact. Because, for example, the Vitis HLS front end is open source. So you can actually feed whatever language you want if you manage to build a wrapper. So you can basically feed whatever language into Vitis HLS, and then it was being put into VHDL. There's various opportunities there. And then Catapult HLS owned by Siemens is essentially the broad support for various FPGAs from various vendors and ASIC. What you got to consider when you have an open source or a vendor independent tool, you may not have as good performance as AMD or Intel itself. But again, on the other hand, I might be able then to use these things for multiple vendors. So it's a trade-off which you have to do again. Do I want the versatility or the flexibility in my future designs, or do I want to have maximum optimizations? Of course, Vivado AMD is kind of nice because Catapult HLS can just create an IP core, and that can be loaded into Vivado then, and then you have the same. But again, sometimes just when the company themselves know that chips themselves the best, although that's not always true. Languages, CC++, System C, OpenCL as well. I'm not going to go too much into detail. I've only worked with CC++ here. Also not extensively because I'm more on a low level end. So I'm not an expert in HLS, but I've worked on the other side. So I've been working with feeding new tools or developing new tools with the help of HLS stuff. CC++, System C. There's also, I've not heard of System C in a very long time though. And there is derivatives of CC++, which Xilinx sometimes calls like V++ or whatever. They basically give you extensions to C++, offering explicit timing and structure modeling, so you can add they have additional features beyond CC++. CC++ may also work though, but you could do more, and so it gives design additional tools in the language. Additional tools, the most important ones. I'm going to come on another slide also again to it. Pragmas. That's going to be the most important thing to make an optimized design in HLS. It's basically you write Pragma and then you write whatever afterwards. I'm going to have to go through the documentation for the list of Pragmas you have. I'm not going to put them on a slide, that's not going to be useful. But basically it's compiler directives. You know, when you have a compiler, you can give them input parameters, and that basically you can use them for unrolling the loops and pipelining, mapping operations to specific hardware resources. So I want to have them on URAM, I want to have on BRAM, I want to have pipelining in my process, I want to have one resource being constantly reused. So the Pragmas will help you to make your design efficient or parallelize it and those kind of things. Synthesis, converting is the obvious tool as before, but in this case it can also mean that we put high-level code into RTL. So depends also which tool you use. It might not even end up in between in VHDL. In our case, it ends up in VHDL or Verilog, but this may not be the case. And validation. Validation is often done I will have an extra slide on it, but essentially the post-synthesis checks ensure if the functional behavior which we have generated matches the original high-level design. So we let the SEEP code run, and we have the simulation, and we get the result, which is basically co-simulation, for example. But it's not the only approach to do this, but it's the most common one. I'm also going to only introduce this one in a lecture. So co-simulation is very powerful. This is nothing particularly new. Basically, you have the similar constraints as you have in a VHDL design, obviously. And actually, this is much more present in such a design because you might write a huge algorithm for a tiny FPGA, and then you turn very quickly out that your resources will run out. So basically, we still have to look out for timing constraints. So we want to ensure timing closure. HLS tool allows us to analyze these things often there. So we do not have to go to the low level. Might not be 100% precise before implementation, but it's something which helps us already to look on that level into these things. So I can already do some pipelining or whatever in my code. Area constraints, analysis of hardware resources required. Also, the tool will give insight into that. And then basically, it's the common thing that we run out of resources. Again, the HLS tool will give us an overview of it. If we're on a border, it might be worth to go through the entire design flow in between and see how bad is it actually. But again, as you're working on such a high level, small things can really blow up. Like, I'm just doing a loop for this, and then it's a ton of logic. So not always easy to assess without. It's a learning curve. You need to have experience in the domain. Performance constraints. You want to have here the balance is always of finding maximum throughput or maximum latency and minimizing latency. These things are not always working in the same direction. So you may sacrifice latency for having more throughput. And HLS allows through pragmas to tune these metrics through different methodologies. So we can adjust the algorithm on our side, of course. I can always write an algorithm a bit differently. Or, of course, through directives to unroll things also. Theme of design techniques. Also just comprehensively on one slide. Pipelining, we know from the previous lecture, is basically overlaps the execution of operation in loops or functions to maximize throughput. So what we do is we start a pipeline, and then each of the so without pipelining, we do each operation separately. So we do the loop, and then we do the next loop. So basically, we do the loop, finish loop, next loop, finish a loop, next loop. What we do in pipelining, we do loop step 1, process goes into step 2 of the loop, and then we already start when it's in step 2 already, we start the next process essentially, which means that we might need more clock cycles sometimes, so it can increase our latency in some scenarios. We encountered pipelining previously for more flexibility, for timing optimization, but here it can be also very much used for throughput, which also applies for VHDL, of course, that it also increases throughput if you do it well. So that's one thing is in the previous lecture, the scheme, resource sharing, as the name says, you basically share resources among multiple processes. So you may want to use a multiplier for multiple applications, but this basically you have here the impact or the trade-off reduces area at the cost of performance. Because you basically, when you use a multiplier and you need to use it multiple times, if you do not do resource sharing, then you will create a multiplier each time as logic. But if you say you do resource sharing, you will use always the same multiplier. This can, of course, actually be very efficient if you do it wisely. You may not use your multiplier constantly in your design. And then if you time it right, you can just have an overlap and it's fine. But it might still, in most cases, will still lead to a performance loss because you've got to be very, very careful and very, very well optimizing to not do this. This is nothing new. this happens and you do this actually also in VHDL design, so I'm not going to go too much into detail here. Loop unrolling, that's actually that's the most powerful HLS thing there is, I think. I mean, obviously you have the two, but that's something HLS specific. You will write an algorithm, and you do execute it sequentially, but what loop unrolling does, it basically can parallelize all these kind of things. Whatever step it will find, it will try to parallelize, and that will increase your throughput and your performance massively. And that's where your FPGA comes in, right? You have resources, I can make everything parallel, execute it as often as I want in parallel. Multiple threads if you want, sorry, it's not the right word, but for software engineers they will understand. Basically this allows me to increase my performance massively compared to a CPU, and that's what I want especially if I use HLS. I do not necessarily care about the perfect performance or whatever. I want to have more performance than I would have with a CPU or a GPU. So I will use loop unrolling definitely.
Question, now I'm not sure how likely it is to happen in FPGA, but sometimes loops are dependent on each other because some variable is building. Will this recognize this?
It should, yes.
It should.
So basically what it does is more like, let's say, sometimes loops can do that, yes. But then there is in the logic already when you code it, there's a dependency, right? Like you feed a value back in or something like this. This will of course be recognized because the logic path will feed back in. It's mostly like when you would go through a pixel and let's say you do something very simple. You wanna, how's it called? I forgot the name now. You wanna threshold your image. So you go through your image and you wanna say below or above threshold. Then I will do loop unrolling and will decide how far I will unroll it because I'm not gonna do all the pixels in parallel, but I might wanna do 10 pixels in parallel, and that's essentially what happens here. Of course, if it's building on each other, there will be a limited unrolling possible depending on how it's being fed back. So into parallels to maximize parallelism and performance. That's what most people these days talk about when they talk about FPGAs actually. That, oh, I can parallelize everything. That's why, because we have unrolling functionalities. And it's something which I was totally oblivious that exists while I was working in VHDL. I mean, you do it naturally, but you do not on VHDL. If you write rarely full-on algorithms because it's not needed these days anymore. But many people still write in VHDL algorithms because if they know this algorithm will be used for a long time, then the design effort is still worth it. So basically, original loop iterates 10 times sequentially. If I do loop unrolling, I can do 10 loops in parallel, and I'm done. Verification and co-simulation, or through co-simulation. What is co-simulation? Already previously mentioned very briefly. Basically involves verifying the high-level C code alongside the RTL code generated by HLS tools. So basically, I feed in the functional high-level model and then see what the tool has generated, if that gives me the same result. So that means that all the test bench and everything will be created on both levels, or at least there is an interface from a C test bench into which is the output is being converted into the RTL input. So basically what happens is the C design is simulated using high-level simulation tools. So we use here model sim or whatever, widest co-simulation. And at the same time, the RTL generated HLS tools is simulated in also model sim or Vivado, for example, or whatever tools they use in the background, right? Doesn't have to open Vivado, you can just use a sub tool. And then basically what is the nice thing about this? It will automatically already compare my results and tell me good or bad, which might not be all I need, so I might still have to dive into it, right? But at least I know that my result is the same. And the more I test in my test bench, the more of this I can be sure that it actually works the same way. If I have just an adder, sure. If I do 1 plus 2, when I do A plus B and I write a test bench to do that in simulation in C++, and then it does it on both sides, then I can be quite right. But if I have an entire algorithm with a lot of parameters feed in, then I need a more complex test bench to make sure that these things work. Benefits, It's, of course, I have very early detection of functional mismatches, because if I do not want to go further into my process to have the same thing. It's also actually very common. Co-simulation, as an example, is sometimes used by when people develop algorithms or encodings in VHDL. So you can write your Python simulation, your Python model of your algorithm, and that's how you develop it, right? You do your R&D, how do I do an algorithm, how does it functionally work? Then you let it run through your image or whatever it is, you get the result out. That's what you store, and that's what you then can compare. We had this in verification and simulation, and then you can compare that to your VHDL simulation output. That would be the ideal, and this does it automatically for you.
Do you recommend to run it after every commit, or
Mm,
you do it several times during development?
I mean, the co-simulation you will run when you just potentially after every commit, as often as you would not run a normal simulation, right? So in the beginning, you will not get any useful output out of this, but I've definitely run it as soon as I have a function. I will run this co-simulation. For what in the process, what other people do, that will only be useful as soon as you have kind of your algorithm already implemented in VHDL. Otherwise, my output is obviously going to be different one than the Python or whatever, MATLAB or whatever simulation output I have. So this is mostly used for verification, or I've designed changes and I want to make sure that this still is correct and behaves as it should.
So maybe it won't be able to implement this as a GitHub action.
You could. Of course, you can make it a CI pipeline or whatever. With a CI pipeline, it's like in unit testing. Usually you wouldn't do unit testing every time, but if you do it with each commit, then you will do it with each commit because it doesn't matter, yes. So this is true, but co-simulation basically is part of the design process itself, and you will run that most likely locally in a sense. Of course, you might want to implement it before someone merges a branch that you run the co-simulation on a server, but then you have to get this running in a CI pipeline, which you could get it all into a Docker and so on. Yeah, it comes with an extra effort where you have to see, do I really need this? Or what design practices do I have in my company or in my team or whatever? Yes, but basically it provides a confidence that the design behaves as expected before implementation, which is very nice. I like co-simulation. And then I use it, for example, to verify my master thesis and my P course, which I developed in another tool. So this can be quite powerful. And then you have the challenges. Synchronization issue may arise, especially with complex designs. So you may not exactly get the same things out because you have like floating point differences or whatever. That can be very annoying, and that's something which one has to then gain experience how to mitigate these things. Of course, and then there might be discrepancies between your high-level simulation, your RTL simulation. So, it is the further down you go in your process. We had this also in VHDL, the synthesis simulation or resource reports are not going to be the same as the implementation one, because you have implemented your design much, much more detailed after place and route. So that applies, of course, here too. So you need to still go through the rest of the design process to be sure that it works. Design integration. Yes. Oh yeah, so basically, there was this one. HLS sounds like a tool which you could use for your full FPGA design. You can, and you can especially if you work with system on chips. Then you basically will never leave potentially your HLS, and you write your C processor code, and then at the same time, this one I want to have running on my FPGA, and you write it almost in the same way. In the same tool, very convenient, so you don't even notice anymore maybe where is what. Of course, that's one way. But often, in most cases, these days especially, still you and you use HLS to create an IP core, and that one you will integrate manually in Vivado into your hardware design. And then you do all the process through there. So basically, as soon as I have them validated via co-simulations, then I need to integrate them into the larger systems, like to my Ethernet, to all these kind of things. So it's something to be happening, although these integrations get much, much easier So with each year and each whatever iteration of the design tools, this becomes more seamless. So basically, yeah, and that's what I'm saying. Essentially, the HLS tools allow for easy integration of HLS-generated RTL with custom RTL or other IP cores, because they would just be exported as an IP core. That's what we're gonna use also in the assignment. And your free assignment, that basically make an IP core, and then you can put that onto your into Vivado and then do the rest of the design process. Interface and communication. There is gonna be directives which allow you to very easily create an AXI interface, and then you can very easily interface between your different design blocks. I think that's quite clear. So this is something to consider, but you gotta consider then the normal things. You gotta have bus interface compatibility, clock domains, handshaking mechanisms, so that your different design blocks will work, especially if you come from your HLS. I have my IP core. It will run, I'm intending it to run at this frequency, but this other one doesn't work, so a different one. Then you need to still implement your clock domain crossing in hardware design potentially. So something to be aware of. Essentially the same design rules as in a hardware design apply for a HLS IP core. It's not magically doing everything. And then integration step is basically you generate and verify your individual HLS block. You integrate the HLS with existing hardware. So you put them all, that's why we learned the block design. So you can integrate it easily into block design, or of course you can just write the HDL code for that yourself. And then you will run a full system simulation to ensure proper data flow and timing constraints. So this is why you then need very huge test benches, because you can always do each of your design blocks separately, but these communication considerations, everything you have to do, and the clock domain crossing, all that stuff, is what you gotta then in the end consider also, and you gotta verify that everything together works. And these simulations will take time. There's not gonna be a way around it, because you wanna run your full block and you wanna see that everything works properly. That's what you do when you verify your design in the very end. And if you have big designs, that's how it's gonna be. Verification, as we said in the lectures before, verification takes time. That's how it is. If you do verification properly, it always takes time. Ensuring that HLS blocks work seamlessly within a larger design system. Obviously, because of the challenge before, I might have different clock domains that might not just work as I thought it would. Sometimes interfaces are a bit different. Sometimes another IP core might use a standard a bit differently, and then others I don't even see. I'm using the same interface, why does this not work? But there's some kind of difference, a tiny one. I've experienced all these kind of things. And then handling, or like you buy an IP core and you cannot change that, and they use it differently. Then you have to adapt everything else on your design to it because you're not allowed to touch it, or because it's encrypted, or these kind of things. And then handling issues related to synchronization, timing, and resource sharing. Essentially what I just said, between the different modules is the biggest challenge, and that's where your time will go. Of course, if you stay in full HLS and you just use the HLS tool to integrate everything, you might not include it, but you also may not notice. That's what the kind of goal is for, if AMD pushes HLS so hard, the goal is to not have to have, for the developer not to have to go into these low levels. But then you cannot include your own IP cores, or not that freely. And then you have to go to this. You can, but then you need to choose a bit of a different design flow. Limitation and challenges, I think they are already quite clear. There are 5 of them. Debugging challenges, as I just said, you may not see everything because you work on a higher level. The higher the abstraction level, the less insight you have. So you rely on high-level simulation tools and not fine-grained inspection. And there might just happen discrepancies between what you wrote in C++ and what comes out, just because of the synthesis tools, how it works. Learning curve. Every new tool has a learning curve, but of course you go here from C++ to chip design. And especially if you work in HLS, you may not know all the things which we talked about in this course. That all these kind of things can play a role if you do your design. So if I come as a software developer and I write my code and I use a Pragma or whatever, to apply things and like, this doesn't work because you have run out of this resource, or you get like errors which you have never heard of. So some hardware knowledge is going to be useful. So basically, hardware designers must still understand FPGA hardware for optimal design, maybe even for getting anything to work. And of course, here switching tools and targeting different FPGAs can be challenging. When you go from AMD to Intel tool will be quite different. That's why we have our vendor-independent tools, but then they will be less optimal. It's all quite challenging. Although this is less of a problem than hardware knowledge, in my opinion. If you have one-time hardware knowledge that will apply for all the devices, you just got to figure out how does this tool do it for these kind of chips. And then resource performance limitations. We have talked about it. You have just a higher abstraction level. That's how it is. You write your code in C++, not on a low level. You will have overhead from not only from like your bit width of vectors or whatever, but you will just have not the insight into leaving parts out. Also, your tool will have an overhead because it has an abstraction level automatically generated. So it will apply certain concepts to this, but it means it's a generalized concept, it's not a perfectly optimized concept. So if you have a certain approach which you apply to everything, then it will not be specifically made for this scenario, and then you will lose performance. So basically, complex custom logic may better be suited for HDL, especially also you come into complex designs. So it's not useful for complex control logic. HLS is just, in most of the tasks which you have seen has a state machine. So if I want to have a complex control system or interfacing of a camera or a SDRAM controller, that's a control system. That I would not write in HLS because it's just going to be, I do not have the low-level bit interface and all this control of these kind of things. So it becomes all much, much more difficult. And it's just not made for this. It's made for algorithms, for encodings, for those kind of things. So it becomes very powerful there, but it gets worse and worse if I want to control a motor. It's simply how it is. So it excels at data parallel tasks, but it struggles with intricate control logic. So that's something to be aware of, where you should use it, where you shouldn't use it. And the less design customization is basically what I said before. Difficult to achieve specific optimization that are easily done in HDL. If that's from vector dimensions to having a certain approach compared to HLS. HLS is a tool which generally applies tools which it knows to a problem, to any problem. But these tools might not be suitable and might not be detect that I could do this genius approach and which saves me this and this much resources. It just doesn't exist. It's a tool which does not understand necessarily what I tried to do. It's not a human, simply put. And then, of course, here a higher overhead for small designs. The HLS tool can have a longer compile times, especially for large designs. But here is the overhead is the bigger one. For simpler design, directly HDL coding might even be faster and more efficient. If I have a very small design and I want to have an AXI interface and this and this and this, then your HLS, so I need memory access, will do this for like 1 byte. It's not exaggerated, but like you might just want to do it and your logic is 1 byte or certain, again, it will try to apply a solution which does not fit my problem perfectly. So and especially this is made for big designs, HLS, for big algorithms, for complex algorithms. And if I just want to do A plus B, I will have an overhead, which it does because it is used to having more complex equations and problems. It's just something to be aware of. Use HLS for algorithms if you do not care about perfect performance. And then you're going to be very, very fast. That's going to save you tons of money. You will be much faster than anyone else in developing when they would try to VHDL. But if you need to then integrate also a SDRAM and a camera and whatever into this, then you have a mixed design approach. I might want to write my algorithm in HLS and then do the things around. So just in a nutshell slide, we have covered all this, I think, in the lecture, but I thought such a table might be useful for anyone who then later wants to go into it. You have here, so basically on the left side, we have the different aspects from abstraction level, speed and development, control over hardware optimizations, tool dependency, performance, and an example, complexity. On the HLS design, we just said it, high level, algorithmic, especially algorithms. It's faster in development and has much, much less code, so it's also easier to dive through. Less control over specific hardware implementation, automatization applies like pipelining, so it's kind of nice. And loop unrolling relies on the HLS tool chain. Also good to know is, for many years, HLS was not liked by many developers from the hardware design community. Why? Because these HLS tools were not good. They were just, you have to consider they need to understand each scenario, and it's a compiler on a compiler. And as we know for example, from Python, when it translates to a lower level, it's just not as fast. It's a different abstraction level. The same applies here. So anyone who wants to write high-performant code in Python says, oh, Python is performant, but if you think about it, NumPy, TensorFlow, and PyTorch, or any of these tools, they translate low in the back end to a lower level than normal Python does. And here you always translate to VHDL and then down. So it's the same problematic, essentially. That you will have some overhead, which you do not maybe want. And then potential for overhead or less efficient RTL. And then example complexity. Simple code tools generates RTL. So that's kind of nice. And then when we go to RTL, it's low-level hardware-centric, so basically every interface to memory controllers, cameras, state machines, overall system control. Unless I use for system control a soft CPU, so a CPU integrated in FPGA, then the control will go through a state machine. It's slower, but it's more detailed. More detailed has its drawbacks. So I have full complete control over design and hardware resources, but I need to do manual optimization. Every pipelining I need to do myself. Every resource utilization I need to do myself. And I have full control, manual RTL coding. So I might even be more vendor independent unless I use certain commands, which also exists, of course, in VHDL, and potential for highly optimized RTL. It requires full specification of RTL. So I need to do everything in there then, and that's where the overhead comes from. And so you see here it's like faster versus slower, but more detailed versus less code. So it's kind of nice. There's always uses. I'm not someone, out of my experience, I'm not like traditionally that people have tried, I tried HLS and they're always disappointed. So what's happened is 20 years there came the first HLS tool and people, oh cool, let's try out. Didn't work. 5 years later, oh there's another one, let's try out. Or still bad. And then every 5 years, so some people stopped looking into HLS because it's just always turned out to be disappointed. But there are clear application scenarios where it just saves so much time, but it might not be interesting for every company as well. Like if you are known for having high performance stuff and you take your time but you're good, then you're gonna stay here. If you wanna go into like server-based or cloud-based things, then you might wanna consider HLS because you have your framework around and you write your HLS code for each time in your algorithm. Yes?
In the industry, which one of those approaches more or how well adapted is HLS by the industry?
Difficult to say, to be honest, and I wouldn't know. It comes here with the application areas. When you talk about space industry, there's not going to be HLS much. It's just historically the designs are older. There's IP cores for full chips, and we're working also with old devices. HLS may not be as well supported for older devices as for newer ones, but if you go into the cloud industry or AI stuff or whatever, the HLS is much more common. But in those industries I'm not in, so that would be my guess. Also the HLS tools. From what I know, AMD has been pushing this since I started. HLS was like here, and now it's becoming bigger and bigger. So they're really pushing it and advertising it because it allows more people to do FPGA design. So I see suddenly you can get a C++ developer to do these designs after they have learned about hardware. So you give them workshop, transfer learning, and suddenly they're a good hardware developer. So that basically, for companies who struggle to get FPGA developers and do not need to be top-notch but want to be more performant, it's a thing. Also, the cloud things are a newer thing. So the cloud processing has rarely existed before the AMD Versal devices. Sorry, the Versal devices is out since 4 or 5 years now. So it's a newer tendency. So it's developing and this is still shifting. HLS very often used for DSP, so digital signal processing. Obviously, it's a very algorithmic heavy task with filters, FFTs, and so on. Although here you got to be careful if you go then to communication system 5G, 6G. If you remember from last lecture, some developers will want to have each femtosecond, whatever, used for in this clock cycle, and this optimization is not possible in there. But if you're figuring out, we have new devices, we want to do now 7G or 6G, you might want to do a first assessment how it works. You implement your new algorithms and you see how much overhead there has. You know, as developer, later when I dive into the code and replace it with my own HDL code, then I can get this and this much more out, 20% or whatever. Then this is a good first estimate. Image processing, very common. Edge detection, object recognition. But there you go, then overlap between, they have very much overlap with GPUs. And I remember when I got into it, I got told like, yeah, we developed this algorithm, but now NVIDIA brought the next GPU, and now we're slower again. So and then you develop again. That's why HLS might be useful, because you're going to be faster, you can use it when you have a new algorithm. Or you just want to have the flexibility and want to do more than just GPU or image processing on your device. Like, you know, you also need to encode it and encrypt it and all these kind of things, and a GPU is not good at it, right? Not necessarily, because it's focused on one thing, and an FPGA gives you the option to have in one device, have my processing, but then also encrypt it back. And that's going to be very, very efficient, of course. Artificial intelligence and machine learning is my domain. I can say yes, but also that's an older trend. These days, you're going to use much, much more advanced tools, which do even on a higher level than HLS. So that's something which we're going to come into the next lecture. Of course, you can write your... So okay, originally when you dive into machine learning on FPGAs, or neural networks on FPGAs, in the very beginning, people wrote there, oh, how much performance can we actually get with our neural networks? They wrote it in VHDL or in the system Verilog, and it's studies of small networks, because you can imagine how much coding effort it is to do a neural network in VHDL from scratch. So they did this and they thought, let's do it in HLS. And that was massively faster, and then it became for some application for researchers, it became relevant because the matrix operations are very, very strong. There was at the times when like CUDA came or before CUDA. So, and then now there's accelerators which you just put an IP core, there's tools like HLS tools which transfer neural networks into VHDLs directly, automatically. I've also done one of these tools as my master thesis, or I've done as a proof of concept. We can have this next week. But essentially, it's something where AI and machine learning had so much push and so much relevance that people decided I will put even more resources onto it, because HLS is not good enough from the development cycle. It would be like writing a neural network in C++. No one does that. So, and that I think is it for today. So there was a big topic, but it's also just to introduce what it can do, and that you have seen it and you're aware of it. And I will show it in the seminar, an example, and you will also get into the tool in the assignment ideally. You do not have to if you prefer to do VHDL. You might miss a point or whatever, but again, you might not need the points. You just need 70%. But if I remember correctly, you don't quite reach the 70% without the last assignment. Good. I think that's it.